Okay. So again, thanks a lot for inviting us for this work on process level power models. So we are going to be to present this work. We conducted this work together.
Yes, so I'm Emile Cadorel. I did a PhD in Nantes a few years back on energy-aware management of scientific workflows, and I'm working with Dimitri.
And I also did my PhD thesis in Nantes in the same team, in the STACK team from INRIA, on understanding the energy consumption of blockchain and in particular smart contracts. And now we are both working at Davidson Consulting as industrial researcher. So we are working also with Massinissa, that you may know. So just a little bit about the type of research we are conducting in our company. So we have, let's say, 3 main projects today. So we are part of the IDF Dozen INR Labcom with Telecom Sud Paris on dynamic slice, dynamic optimization and orchestration of network slicing. And we also have one INR called Distiller with INRIA Spirals in Lille, OVH Cloud and Orange. And we are currently working on cloud native application and how to reduce their impact. And at Davidson, especially, we are working on caching systems and memory usage. And we are also part of the Power API consortium. So we are going to talk about Power API also today. And we are working on evaluating current models on how to estimate the energy consumption of software. And that will be our main focus today. So, as I said, today we are going to talk about the energy consumption of software and how we can measure it. So we are going to try to define the notion of what it means to say the energy consumption of a software. And we are going to see that it's not that easy to define, and that if we try to provide a more formal definition of this concept, we can actually find a lot of interesting things about the limitation of current state of the art regarding how to measure it on a server. So as I said, the main topic we are trying to address today is that we want to measure the energy consumption of a software. So generally, the main hypothesis behind this is that if you can measure the energy consumption of your software, and maybe you can try to optimize, you can try to apply maybe best practices if you are in a company to try to improve and lower the energy consumption of your software. And if you want to do that, today you have 2 main possible approaches. You can measure the energy consumption either at the server level or at the process level. So at the server level, it's maybe the most straightforward way to measure the energy consumption. So you can either do it with a physical device, for example, a smart PDU or a power meter. So maybe if you are using a Grid 4000, there's a lot of different clusters that are monitored using power meters. And you can also use embedded sensors such as Intel Ripple. And so it's a feature of modern CPU that can let you get the energy consumption of your processor. So the main advantages of those approaches is that the measurements are considered reliable. So for power meters, basically you have the measurement at the physical level, so you cannot be much more precise. But even with Ripple, the general consensus is that those measurements are considered quite reliable. And the disadvantages are that the measurements are done at a fairly low level. So you can either have the measurement of the whole server or the whole CPU. And if you want to measure the energy consumption of multiple services on the same server, then you can't. You can just have the measurement of your whole CPU or whole server. So nowadays, people want to have the measurement of their own processes. And for example, if you have a microservices-based application, you have several services running on the same server. Or in generally, for the cloud computing, this is it. You have several services on the same server. And so to tackle this issue of having per processes measurement, a small ecosystem of software sensors has emerged. And the approach is always the same. They take the energy consumption of the server and they split it among various monitored processes. So advantages should give process one measure per process. And the disadvantages is that it's based on custom models, and those models are currently unevaluated. So there's three main technology in the state of the art. PowerPI, developed by INRIA, that uses a linear regression and performances counters. Scaphandre is an open source project, and Kepler, that is developed by Red Hat and mostly focused on Kubernetes. So Scaphandre and Kepler, they basically uses CPU time ratio. For example, if your process consumes 50% of the CPU time, then it will be considered as consuming 50% of the energy. And PowerPI is a bit more complex. It uses performance counters. And this model provides different results. And the issue is that how can we compare the results of those models? It's a bit tricky because there's no physical measure to compare with model to find out if those models are precise or not, because there's no physical server, physical device inside the CPU to know precisely which process consume how many energy. And so currently there's no evaluation, and for us, if there's no evaluation and no reference value, it's because we didn't spend enough time defining the notion of attribution or the notion of energy consumption of a software. And therefore, we can't have any expected outcome of this model. So we are going to try to understand how application generate energy consumption of a physical machine. So in order to understand a bit more how server can consume energy for a given load, we conducted experiments using a stress application. So stress applications are small processes that do always the same thing and a very simple thing. So we used we selected 12 functions that are presented here. So for example, type conversion, implementation of well-known algorithm, conditional jumps, etc. So those functions are very stable and they always used 100% of the assigned CPU core. So if you run a stress function on one core, it will use the entire core for the whole workload. And these are very stable functions. So here, and we use two servers, one called Ptero, which is a small server, and one called Dau from Grid 4000, which is a big server, and a bigger server. So here, for example, we launched all the stress functions on 0 to n thread to use from 0% CPU to all the CPU. And so we deactivated hyperthreading and turboboost. So we only use physical core. And yeah, so basically one process per core from 0 to max number of cores. And so here on the figure, we can see that, and also it's important, we don't have any contention. So we don't have like two processes fighting for the same core. So there's no contention at all. And we can make several observations. So for the same CPU load, we have a very high variability. So on Dau, on the bigger server, you have a 12% variability if you use all the cores. So 12% between the program that consume the less energy and the one consuming the most energy. And you have 20% variability on the smaller server. So that means for the same percentage of core used, you can have different consumptions depending on the type of workload you're using. And also the order of consumption between functions, it varies between servers. So for example, on the smallest server, float64 is the most expensive program, but on the biggest server, matrix prod is the function that you consume more energy. So a given program, even if the program is very stable, it won't consume the same energy on different servers. And even if you have a list of programs, the orders of consumption will be different depending on the servers. And also, one key observation is that there's a big difference between idle power consumption and the power consumption you have at one core. So actually, on the figure here, the smaller at 0%, you don't have it's the energy consumption in idle, so just have the operating system and no activity. And then when you start the first to use the first core on your server, you have a big jump. So for example, here from 29 watt to 110 watts. So we called this consumption residual consumption, and it doesn't depend on the actual load. It's just here because you start to use the core on your server, and then when you turn on the first core, then all the cores, the consumption of all the cores are quite linear, and it's a function of the load. So you have a linear energy consumption. And so this residual part is very important for the rest of the presentation. So we wanted to try to define what do we mean by consumption of an application on a server. So we can first consider a naive definition of what is meant by consuming energy for an application. And this naive definition will be the following. The consumption of an application is the consumption that would have not been observed if the application would have not been executed. So for example, here, let's say you have the residual consumption here in pink, and the active consumption, the linear one, in blue, of two applications running together. And then, let's say you have here the consumption of if you remove one application, you can observe this the consumption, and then the difference between the server with all the application and the server with all application X minus the application you want to measure, then we can consider that in green here you have the consumption of the application. So this is it. So it works quite a bit for if you have a linear energy consumption, you can just subtract the energy of all the processes. Then now we have to think about what we can do with the residual energy consumption. So that's the same issue with idle, but here with the residual energy consumption. So we don't really at the moment. Yes.
May I ask a question on this? It's a bit contradictory with what you said before, with what you tried with some functions that take the 100% of the core in all the capacity of the CPU if it is available. Because here, if you have a sharing of the CPU between two processes, then maybe if you remove one application, then the other will consume more because it will go faster, because it will try to consume all the CPU that is available.
So for the moment, we deactivated hyperthreading and turboboost. So here on the figure, you can see that if you remove the second application, the first one will not consume more.
Okay.
It will consume the. We actually have this this phenomenon where the active part of the application is just added to the complete consumption of the server. But there is a question that stays is what do we do with the residual consumption.
Yeah, for
Because
sure, there will be this question for sure. Yeah. But I have another question. Did you try, so if you have two applications, did you try to remove one and the other and do the green parts for each of them? When you add them, you get exactly what you have
that's
in what you have the two.
exactly what we did with this figure. We added one thread more each time until we reached 100%. And we did that with different kind of stress functions, and we had linear consumption with that load.
But you are right. It only works with without hyperthreading and without turbo boost. And actually,
we will come to
we'll
that.
come to this part.
Okay, thanks.
So actually, if you don't have hyperthreading and turbo boost, you could consider that this definition, this naive definition, could work, and maybe you can try to find a way to split the residual consumption fairly across the different applications. However, it's a bit more complicated than this. This residual consumption between 0 and 1 core, it's actually tied to the frequency of the fastest core among all cores. So you may know that cores can work at different frequencies, but the residual consumption, it will be linked to the frequency of the fastest core. So we can see here the frequency of the fastest core and the residual consumption here in watts, and you can see that it increases with the frequency. So at nominal frequency, the residual is 15 watts, and actually it's 15 watts more than idle. Just here because we start the first core. So, for example, if you have two applications running at different frequency, and it can happen, for example, if you have one application that have pauses because of, for example, I/O, thread synchronization, sleep, etc. Then we don't know what to do with the residual consumption because here, for example, here you have two applications, A and B. B has the highest frequency, so it has a bigger residual consumption. And then when you run both A and B on the same server, then the residual consumption will be equal to the residual consumption of B, because B is running at the fastest frequency. And A will have let's say a bigger residual consumption, not because of its own activity, but because of the activity of the application B. So we were working on the easy case without hyperthreading and turbo boost, but actually on a real server, we want to activate hyperthreading and turbo boost. So here we did the same experiment before, but with hyperthreading and turbo boost. So also same case from 0 to 100% CPU. And here we have contention. So because we are using CPU logical cores, so that means that we can have two processes on the same physical core. So that means the maximum execution time will actually be bigger than the smallest execution time. All the applications are not running at the same speed, because when you have two processes on the same core, they take longer than if they were alone. And so here the active power curve is no longer linear, it's more logarithmic, and the server is more energy efficient at highest load. And yeah, you can have here this logarithmic curve. So we observe that the residual consumption is still present, and as I said, we have a logarithmic curve for the active energy consumption. So that means that now the sum of the isolated active consumption is no longer equal to the energy consumption we have when we run all the processes. So if you take the energy consumption of A alone, B alone, and then you run both application, now the sum will be lower. The consumption of the both application running in parallel, it will be lower than if you take the energy consumption of both application separated running on alone. So now we have another question, which is how can we distribute this decrease of the energy consumption? Should we split it fairly based on the isolated active consumption? Should we consider that the application starting first is the one responsible for the decrease in the curve? It's open questions. So all of this, it conducts to one key observation that is really important if you conduct experiment on energy consumption of software using this kind of model. Is that power consumption of a process, it will depend on the deployment context. So what do I mean by this? Let's consider three processes, 1, 0, and 2. Process 0 is running for the whole experiment. At first, it's running with process 1. Then process 1 stop, and then we start. We wait a bit and start process 2. And if you run this kind of experiment with division models, you will have this kind of curve in the energy consumption. So first, P0. So you will observe that the energy consumption profile of the process 0, it will increase when it will be alone on the server, and then it will decrease back when P2 is starting. So this is because of the fact that we explained before. The process is the server is more energy efficient when it's loaded. And now, even though process 0 is a stable process, like a stress function, for example, the energy consumption is not stable just because of the context. So that's important to know if you're using this kind of models, if you have an experiment related to energy consumption.
I have a question on this, sorry.
Yes.
So here, what you are looking is the power. But as
Yes.
you know, what is counting is the energy. So my question is, in the middle, of course, P0, the process 0 consume more in terms of power, but maybe it goes faster and then it does more things. So how do you take this into account?
We have an experiment on that, on exactly that at the end. But as we said in this slide, the increase in time does not compensate the decrease in power. So if you don't take two times the time when you have contention, so you are more energy efficient at high load.
Okay.
Not just more power efficient, you are also more energy efficient.
Okay.
So to summarize, there's several points to be cautious about when we define power model. So first, you have a poor correlation between performance counters and energy consumption. If you want to have like a perfect model, you will need to be able to understand exactly which instruction consume which amount of energy. If you just take into account CPU load, then you will have a high variation. There's
yes. So there's 4 points. You have poor correlation between performance counters and consumption. Because the energy consumption is dependent on the context, you can't really do software optimization because you will see some increase in your consumption that are not related to your application, but on the deployment context. And there are also two political decisions on what do you do with the residual consumption, and who is responsible for the decrease in the logarithmic curve. Because if we have multiple applications, we are more energy efficient. So it's better to have collocated applications than application running alone. But who is responsible for that? So that's a political decision to decide to which application we will assign this decrease in consumption.
We call that political because there's no like single value of truth. It's not like technical precision, for example. You could be the first 2 points are technical. You can have you could have like a perfect model on a perfect computer that give you perfect measurements. But the last two, it's up to the model designers to document those choices.
What we are trying to do in these definitions. So if we establish the decisions we are making with these political decisions, we can define some definition of what do we mean by software consumption. For example, if we decide to assign the residual consumption based on the ratio of the isolated consumption of the application, we then have a definition of the software consumption. And what is important is that we have a truth value, and we can compare the model to something that is what we are expecting from the models. Which is a point that is lacking for the moment in the state of the art. There is no real evaluation of the expected results. The only evaluation we found is based on if we do the sum of the consumption of the programs running on the server, we have the consumption of the server. So our model is right. But we don't really completely agree with that. So that's why we are defining a truth value with these definitions. We can do some other definitions, but I think we may skip that to go directly to the evaluation because we don't have many time. So here it's the evaluation of the power models we found in the state of the art that are Scaphandre and Power API. We did not evaluated Kepler because it was it is focusing on Kubernetes, and we wanted to have an environment with the less side effect as possible for our measurements. So the first evaluation was made on the 12 stress functions we already presented. And the protocol was to run the application alone and then in parallel in pairs to get their estimated consumption according to the power models and see if we can extract some truth value from that and compare it to what we can expect from the definition we defined. So in this first evaluation, there is no hyperthreading and no turboboost. So the first evaluation we can see here is on the Tero node. It's the small desktop machine we have with an Intel Xeon CPU. And what we can see is that on the x-axis, we can see the expected results based on the active consumption of the two applications. So if we are equal to 0 on that axis, it means the two applications consume the same amount of active energy when run isolated. If the number is negative, it means the application A is consuming more than B, and if it's positive, it's the contrary. In the y-axis, you have what the power model gave us as a result. And what we can see is that even if the application was consuming 60% more than the application A was consuming 60% more energy than application B in isolated execution, the power model does not see that. And because it's based on CPU time, decide that the two applications are consuming the same amount of energy. Same amount of power. And on the second figure, we did the same experiment, but this time the two applications we executed in parallel were not of the same size. So, for example, application A was using only one core against an application B that was using 3 CPU cores. And we can see three clusters based on the amount of CPU time that the applications are using. If we run this was the result for Power API, and now we have the result for Scaphandre. Yes, we can see that the results are quite similar on Ptero, which is relatively expected because they use relatively the same system of division. We executed the same evaluation, but this time on DAU, which is a node of the Grid 5000 cluster. And what we can see is that for Power API, the model is completely lost. It gives results that are far away from what we could expect from our evaluation on isolated executions. For example, we can see that according to the model, A is consuming thousands times more than B, when actually they are consuming the same. So the reason behind that is because we found what I think is bugs in the model Power API, where the model does not always give the same results for the same entries. As an example, we run 2 times the same execution with 2 stress functions, float 64 against matrix prod. They are the same size, and in isolated execution, they are consuming about the same amount of power. So what we should expect is from both applications to have relatively the same amount of energy consumption. But on the first run, Power API said that matrix prod was consuming more. The second run, with exactly the same configuration, Power API said the contrary. We ran the same experiment with Scaphandre. Scaphandre has had expected results, the same we had with Ptero. And now, in this last experiment with stress applications, we made the frequency of the stress functions vary by capping the amount of CPU time available to one of the 2 applications. Here, the application A had only 60% of CPU time, which made the isolated execution made the frequency of the CPU core decrease. So instead of running at 3.2 gigahertz, it was running at 2.4. thus the ratio of isolated consumption depended more on the residual consumption than on the active consumption. And because of what we said earlier, we can't just consider that residual consumption is not part of the application consumption, because it is due to the amount of work generated by the application. So in this experiment, we considered that residual consumption was part of the application consumption. So that's what we did in the sequential baseline. We used the complete server consumption of the isolated execution, and we did the ratio between the two. And in parallel, we just take what the here Scaphandre said about the ratio. So we can see that it does not follow the ideal line, which is in black here, the line in black, which is y equal to x. And on the right figure, we did the experiment we did earlier with the two applications uncapped, running at full frequency. And what we can see is that Scaphandre does not consider at all residual consumption, and divide only by CPU time, which made application of different sizes have a different consumption, even if they have the same residual consumption when running alone on the machine. Okay, so that was an evaluation on power consumption, but as we said earlier, power consumption is not the only thing we want. We also want energy consumption evaluation, because the consumption of the machine decreases at high load, but as you said, the CPU time should increase as well. So does it compensate the decrease in power consumption by running longer? So for that experiment, we used 4 applications from the Phoronix test suite. It's benchmarks for CPU evaluations. We selected these 4 applications because they have a behavior that is reproducible. When we run the applications multiple times in the same context, we always got the same results in terms of execution time and energy consumption. We used the same servers. So here we have the actual behaviors of the applications when they are running isolated on the Tero machine. Those results were retrieved with the APL Intel system. And what we should consider is what is important here to see is that Cloverleaf is an application with 4 stable phases, yes, and Build 2 has 2 relatively stable phases. Compress has 12 of them, and Da Capo has a surge of consumptions. So we run the 2 of the applications in parallel on the Tero machine. This time we reactivated hyperthreading and turboboost. So here we are using 6 CPU cores per application, so 12 in total, when we have only 6 physical cores, so 12 logical cores on the Tero machine. So there is some sort of contention, but hyper-threaded contention. Not we did not use more than the number of logical cores we had on the machine. So if you remember, build 2, which is here in yellow, had two stable stages that we don't see anymore because the application is mimicking the surge of the Takapo benchmark. So we can't if we want to optimize the program build 2 from a, I don't know, developer perspective, we see some surge in consumption. So we tend to want to know why they are here. Let's say, for example, we are in a cloud context where we have a VM running our build 2 program, and we don't see the deployment context. And another user have a VM on the same server running the Dacapo. We don't see its consumption, so we can't make the relation between the two energy consumption, and we can't know why we have those surges. It's important to note that Scaffold and Power API claim that their models are usable for cloud computing. Here we have the same execution, but this time with compress against Cloverleaf. We see the same problems. If we remember, Cloverleaf has four stable phases. Here we don't see them. And for Power API, we have the same problem we had earlier with the problems of consistency in the Power model, where it is not. If we give it the same entry multiple times, it will give us multiple different results. Here, in time 0 and time 200, we should have almost the same energy consumption because the program was repeated multiple times, but we don't see that in the results of Power API. And last information about this experiment, in all the we run applications a lot of times, and in all those evaluation, we got many different energy consumption for the same application. For example, the Cloverleaf energy consumption ranged from 36 kilojoule to 28 on the Tero machine, which is quite a great variation. And on the Davidson machine, which is a bigger machine, we had a variation of more than 50% of the actual energy consumption of the application. That means that the actual behavior of the application had less impact on the energy consumption than the context. And if we have a bigger machine, we can expect to have even higher variations in that regard.
So there are several things to conclude about this matter. So we still have this issue of allocating the energy consumption of your whole server among different applications. It's not just a problem of not a matter of accuracy, and not all models are equals. It's important to know when you are using this kind of model for the energy consumption of different processes on the same server. It's not just about the frequency of acquiring the measurement. It's not just about having a model that is able to have a complex model based on performance counters. There's a lot of different results here. That's important to know. Those models can be different. And even if we don't have a straightforward way to compare this model, that doesn't mean that we can't compare those models. Those models can and should be evaluated and compared to help users understand the results they're getting. And here, for example, all the experiments we conducted helped us to understand a bit more about server energy consumptions and the limitation of those models. Especially that those models make decisions, even if the decisions are unconscious. The models are here, for example, about how to split the residual consumption, how to split the reduction in the logarithmic consumption curves. And this model, we believe, needs to be documented so that users don't just use this model and get results without understanding how the results are obtained. And it's also, we conclude also that there's no just one single attribution model. And we could have different models depending on what we are expecting for this model. So we see, for example, two main reasons. So first example, if you want to optimize software and reduce the footprint in energy consumption, then you need to be able to understand the profile of energy depending on the activity of the actual activity of the software. So you need measures that are correlated to the usage of the server by the software. Or for example, so that's one usage, and another usage is for people that are making, for example, a life cycle assessment of the software, where here you need to take into account the execution context. And here you don't really care about having a curve, energy consumption curve that you can understand. Here you are interested in how much energy the software is using in its own deployment context. And here the cost could be considered abstract. And those both concerns seems impossible to reconcile. So you can't have a model that can be used to optimize your software, but also to have measure what is dependent of what is linked to the execution context. So that's especially important to know in the context of cloud computing, where you have a different application on the same server. Also, those applications are hosted inside virtual machine, and you are in your own virtual machine, and you don't have any vision of the execution context. So that's it. So yeah, I believe it was quite dense. So if you have any questions about things we are not clear about, feel free, and we can go back to the figures and the facts we highlighted.
So thank you very much for your presentation.
Thank you.
I just will ask, are there any questions in the room? Are there any questions on the bridge? Don't hesitate to ask questions. So I will just finish with one question on my side, one question and one comment. First, one comment. With all what you did, it seems to me that it is really difficult to attribute energy consumption in a cloud environment. So you choose some very simple, but it's normal, very controlled and quite simple scenarios. But even with these scenarios, what you show is that there are some discrepancies between different models and very large differences in the attribution of power consumption. So do you think that this can be improved in the future? Are you working on it? And or is it something that may be difficult because it's a too complex system?
So one type of research we try to conduct is to try to think about if we could build a model, energy model, that would give you an estimation of the energy consumption of your software if it was alone on the server. So here we tried to eliminate all notion of context. And we believe that if we could build such a model, so for example, by instrumenting your code and being able to know what are the instructions you are executing, the frequency you are running on, the nominal frequency if you are alone, etc. If we could have this kind of model, then we could do energy optimization in a cloud context. But it's difficult. We don't know if it's something that is possible or not. And so for the moment, we consider that for researchers and practitioners, if you want to have a measurement on the energy consumption of different processes, for example, with microservices-based application, we tend to advise to run the application on different servers and one application, one process per server. That's the way we would do software optimization. Yep.
Okay, thanks for the answer. And I think a bit the same as you. If we can optimize the software in an isolated context, then one can hope that if it works with many other applications aside, that the optimization in the case of being alone, it should be not also close to optimal for its part of consumption for when it will be with other. This one we could expect, but we don't know, in fact.
Yes.
Yeah. And we can have programs that we did some. So for the moment, it's just a thought. But what is the acceptation we can have when we are doing isolated energy optimization? When we run that on the cloud, will we see some problems? We have the first idea that come to mind is if you optimize the actual CPU power efficiency by doing some caching system on a local execution, you will see a decrease in energy consumption of your program. You may think that you are doing something good in that matter, but when you're deploying that in the cloud, because you are using more memory, maybe you will have a bad impact on the cloud provider orchestration, and then you will actually increase the cloud energy consumption. So
Okay.
I don't think it's that simple to answer, but yes. So for the moment, we don't have many clues on how to avoid that.
So this confirms that it is a very difficult problem. Yeah. Other questions? Last chance on the bridge. So thank you again.
Yeah, thank you.
Thanks a lot for inviting us for this presentation.